want to make sure. So I want to be fair to everyone, and I also want to make sure that we have the problems on time before the exam. So I don't want to have an accumulation of 39 problems the night before the exam or something like that. I want to have them little by little. So please check. I'll add more problems today, so more people. So if you're next in the list or very close, you should get an assignment today or in the next few days. Okay. Let me see. So, who's my pen?
So do you have I have a question. Do you have an exam coming up?
Yeah.
What day is it?
Oh, for the people who already have an assignment, it's due this Saturday. But so I'm trying to give everyone about a week to have your problem ready. So if I assign some today, they're going to be due in a week from today. Okay. And I'll just keep assigning so that so that I make sure that I can give feedback to everyone in a timely manner. So for people who already added answers, I had some feedback already. If you want to go back and check, that was in wiki 3. I also make the wikis shorter, so each wiki now has about 5-6 problems, so that there is no problem with the people accessing at the same time. Hopefully, it will be fine. So expect about a week for any problem from when I assign it. So you'll see in the list that I have your name, the problem you're assigned, the wiki. It belongs to the date I assign it, and the due date. And you can always ask me for feedback. If you get a problem that's absolutely impossible for you, or if you know that you don't have enough time to have it ready for the due date, you can always use your pass. Everybody has one pass. So if you find some, if maybe you know how to do every single problem except the one that I assigned to you, that's fine. Just use your pass, and you'll get in the next round. You'll be the first one to get a problem. Which doesn't mean that it's going to be like an easy problem from the next topic. It's just as we go, whatever we're covering. Once we're done with the list the first time around, then I start with people who use their passes. Once that people are covered, then I get started with the order. Mm-hmm. Okay, so let's see. So first, let me show you what we were doing before. We were working on the pizza problem activity. We went all the way to question 4 very slowly. But so question 4, hopefully we can finish that today. I'll go a little bit quicker. Just as a warm up, I guess. We'll go over question 5. I had a question by email. Since we're here, I'll just answer that question here. So how when we use the product rule or the fundamental counting principle, we're multiplying things. That's because that corresponds to the tree that we have, the branches of the tree. For every branch, you have a certain number of smaller branches coming out of it, and then smaller branches coming out of it. And that's why you have that multiplication. But here, when we went over this one, for example, for the total variety of pizzas, we added. So the question is why we're adding here and not multiplying. This is because we're not combining in any way the cheese pizza with the one topping pizzas. We're just counting. We're just adding to the list. There is one of these and there is 9 of those for a total of 10. If we multiply, we in a way are making pairs. One cheese pizza and one topping pizza together. How many pairs we have? That will be multiplying, counting pairs. So multiplying these first 2. So multiplying all these numbers, 9 choose 0 times 9 choose 1 times 9 choose 2, and so on, will be like lining up a cheese pizza and then a one topping pizza. We have 9 choose 0 topping, 9 choose 0 choose one possibilities, and then a 2-topping pizza, a 3-topping pizza, a 4-topping pizza, and so on. That would be like counting strings of pizza. That would be huge. But we're not doing that. We're not combining them or putting them together in any way. We are actually we're actually just counting how many of each type. That's why we add those numbers. Mm-hmm. Anyways, we did up to part 4. We're gonna go over 5 and on. So I have a poll for numbers 5 and 6 together. Number 5 says, actually, let me use another page, a clean page here. So we're gonna go from 5 and on. Uh-huh. So number 5 says, how many 5-topping pizzas are there? And then number 6 says, how many varieties of pizza with at most 5 different toppings are possible? So what do you think? I launched the poll, so if you could choose one of those. Mm-hmm. So remember that the binomial is just the definition of the binomial is choosing a certain number of elements from a certain number of elements that are available. So good. So I'll just wait 30 more seconds. All right. Good. So most of you are getting it correct. I'll share it with you in 5, 4, 3, 2, 1. Okay. So here you go. So those are the correct options. Oh, I cannot. Could you actually see the entire row? You know, where this sum ends, the 9 choose 0 plus 9 choose 1. Like, I cannot make my window bigger. So I'm not sure that you were able to see where it ends. It ends in 9. Were you able?
Yeah.
Oh, okay, good. So I'm not able to see. I don't know how to make it bigger. Anyways, it ends in 9 choose 5. So.
Oh, I had backwards. I chose 9 choose 5 for 1 and 9. Or, no.
Oh, okay.
No, I chose 2 to the 5th power for 1 and 9 choose 5 for 2, which I think it should have been the other way around.
Let's see. So, how many 5-topping pizzas are there? We need to choose 5 toppings out of the 9, right? So that's what we're doing. We're choose 5 toppings from the 9 available. That's exactly the number of ways to do that is exactly the definition of 9 choose 5. We're choosing 5, 9 available. 9 from the 5 available. That's just it. That's the definition. Mm-hmm. And here it says how many varieties of pizza with at the most, right? So the previous one was exactly 5. This is at most 5, which means that we can choose any number between 0 and 5. So it is okay in this case to choose a 0 toppings pizza, so the cheese pizza. We can also choose a 1-topping pizza or a 2-topping pizza or a 3-topping pizza, a 4-topping pizza, up to 5. So at most 5. That's where the sum ends. Mm-hmm. Yeah? Good. Huh. Okay. So let me see. Let's do 7 and 8 with the poll, and then we'll do the others without the polls. So 7 is how many pizzas with an even number of toppings are possible, and 8, how many with an odd number of toppings are possible. Oh, did I launch it? I didn't launch it, huh? Okay. Because I don't have any answers. Okay. All right. Doing good, doing good. I'll give you 8 more seconds. 5, 4, 3, 2, 1. Okay. So here you go. So pretty good. Those red lines are the correct ones. So, and I'll tell you why I added the other ones as distractors. So, an even number of toppings, that means that we can have 0 toppings, or 2 toppings, or 4 toppings, or 6 toppings, or 8 toppings. Mhm. Now, this sum, mhm, um, the sum of all the possibilities was 2 to the 9. But for an odd number of toppings, it's not clear that this should be 2 to the 5th. Okay? Maybe it is. But let's see. This is an even number of toppings. This one right here, odd number of toppings. I can have 9 choose one topping pizzas, 9 choose three topping pizzas, 9 choose five topping pizzas, and 9 choose seven topping pizzas. Mm-hmm.
And why do we not include the 9 choose 9 option for the odd numbers?
Oh, thank you. Yeah, and 9 choose 9. Thanks. Yeah, that's also allowed. Okay, so I added as distractors the 2 to the 5th and the 2 to the 4th, thinking that maybe somebody will say, oh, I don't know why I added the 2 to the 4th for the other ones. Maybe because I also excluded the 9 choose 9. I don't know. I don't know. But, I said, oh, there's an even number of terms here, or an even number of ways to have an even number, 0, 2, 4, 6, 8. So I thought that was a good distractor. Thinking that maybe if the sum of 9 choose 0, 9 choose 1, all the way to 9 choose 9 is 2 to the 9, maybe this one should be 2 to the 5th or something like that. But that's not really true. In fact, look, we're going to start looking at some properties of binomials, and it is true that n choose k is the same as n choose n minus k. So for instance, 9 choose 0 is the same as 9 choose 9. And they're equal because if you use the definition, the algebraic definition of this, this is just the denominator is k factorial times n minus k factorial, which goes with either one of these two, right? It's symmetric here. So these two are always the same. Therefore, 9 choose 0 is the same as 9 choose 9. 9 choose 1 is the same as 9 choose 2. 9 choose 3. Well, yeah, I don't know why it's skipped. But 9 choose 2 is this. Oh, what am I saying? Wait. So this is not a 2. So 9 choose 8. And 9 choose 2 is the same as 9 choose 7. 9 choose 3 is the same as 9 choose 6. And 9 choose 4 is the same as 9 choose 5. So, for instance, this one is, yeah, go ahead.
That's the answer for number 9, right? That's the explanation for number 9.
Well, actually, No, the explanation for number 9. Let me see. Oh yeah, but they're the same number of 3 topping pizzas than 6 topping pizzas. Yeah, so that would be the explanation here, right? So for this one, 9 choose 3 equals 9 choose 6. Yes, thank you, Amber. Yeah, so that would be the explanation here. So these are the number of 3 topping pizzas. This is the same as 9 factorial over 3 factorial times 6 factorial, which is the same as 9 choose 6, which is the same as the 6 topping pizzas, right? But in reality, what I really wanted you to think about here is, regardless of the formulas, why is it true that the number of 3 topping pizzas, is there any other explanation why the number of 3 topping pizzas is the same as the number of 6 topping pizzas, regardless of what this is, That would be like a combinatorial proof of this statement rather than algebraic. Okay, so I'll go back to that. Let me just say something that where I was going with this. Here, you have the 9 choose 0, the 9 choose 0 here, and then 9 choose 9 there. And then you have the 9 choose 2 here, and the 9 choose 7 there. Those are equal, right? And then I have the 9 choose 4. I have the 9 choose 4 and the 9 choose 5. And then I have the 9 choose 6 and the 9 choose 3. And then I have the 9 choose 8 and the 9 choose 1. Right? So these two sums are actually the same. You see? Mm-hmm. And the total sum for all of them combined was 2 to the 9. So this one is 2 to the 9 over 2, and this one is also 2 to the 9 over 2. So both of them are 2 to the 8. And just as a note. So it's not 2 to the 5 or 2 to the 4 as one of some of my distractors. It's 2 to the 8, each one of them. So I didn't ask for that, but just that curiosity. And we're gonna see more about that later. Now, going back to my explanation in part 9 is, of course, we can do it with the algebraically, right? So both of them, we can actually get the number. Both of them are this. Mm-hmm. However, I wanted to find something more, less algebraic, more in context. So how can I say that there are the same number of 3 topping pizzas and 6 topping pizzas? Well, there's a 1-to-1 correspondence between 3 toppings and 6 toppings. If I choose any 6 topping pizza, my selection of 3 toppings also gives the ones that I'm not using are 6 toppings. Mm-hmm. So every time that I choose a 3 topping pizza, the toppings that I'm not using will make a 6 topping pizza. Mm-hmm. And vice versa. So there is a 1-to-1 correspondence between the 3 topping pizzas and the 6 topping pizzas, because for every 3 topping pizza, all the ingredients that are not used in that pizza could make a unique 6 topping pizza. Mm-hmm. And it's the same explanation here. Oops. It's the same explanation here. Oh. So even if I don't use the formula, the algebraic definition of n choose k and n choose n minus k, selecting k elements, to select k elements, I can as well select the ones that I'm not using in n choose n minus k ways. Okay. So number 10, in how many ways can you order 3 different pizzas for a party? It says different, right? So different pizzas for a party. So
I have a quick question.
Yeah, go ahead.
For number 9, what would be the final answer? Whatever you have to your right? like that?
Well, many times you'll see that there are some problems that say prove this combinatorially and then prove this algebraically. This is what I consider an algebraic argument. You're just saying the actual number is computed this way for both of them. If you're explicitly asked for a combinatorial argument, you can say that selecting 3 toppings to be used in the 3-topping pizza is equivalent to selecting the 6 toppings that won't be used in the pizza. Something like this. And so this gives you the 9 choose 3, and this gives you the 9 choose 6. So that's what is considered a combinatorial argument.
Oh, okay, so that would be like the proof if you were
That
to
would be like the combinatorial proof. The other one is also proof. This is algebraic. This is an algebraic argument. Same as this one. This one is algebraic.
If you were, depending on the question.
Yeah. So I'll show you, for instance. Let me see if I have them here. Maybe here. Oh, maybe not in this one. I don't have B here. So I'll find the problem, the specific problem that you can see that. There's several ones, but there is one that I have in mind in section B that tells you, that reads exactly something like that. See, yeah, so for example, problem B70, you can take a look later. See problem B70 for, combinatorial versus algebraic explanations. So here in the, for number 9, I didn't tell you how to explain it, right? So either one is fine, an algebraic argument or a combinatorial one. But in problem B70, they explicitly ask you to do it in both ways. Yeah. So that one, the algebraic one, most people are more familiar, providing algebraic arguments, but not necessarily combinatorial. But we're trying to learn combinatorial ones because, as it happens, there are things that are really, really hard to prove algebraically, but are actually very easy to prove combinatorially. But, it requires a clever argument, but once you see it, it's pretty easy. So we're trying to learn, we're forcing our minds to think a little bit differently, not depend so much on algebra, because as powerful as it is, sometimes the algebraic proofs actually happen to be really, really hard compared to the combinatorial ones. That's the power of combinatorics. So we're trying to learn those.
Thank you.
Yeah, so it's a good question. Like, I didn't require you to do things in a certain way here. Both are valid, but in that problem and others, you are explicitly asked to use one or the other.
Oh, so earlier, did you say problem 370 for algebraic versus
algebraic versus combinatorial explanations? Yeah. So in this 70, they're asking you to prove something, an identity, in both ways. part A is also likely. Mm-hmm.
Yeah, I just meant the number.
B,
Is it
B.
1370 or just
No, B.
37?
Section B. Section B as in boy, 70.
Oh, okay, section B. Okay,
Yeah.
thank you.
Section B, problem 70. Okay. So, again, I'll make this small when, before uploading so that you get everything. But here I want to focus on this part. So, problem 10, in how many ways can you order 3 different pizzas for a party? So, this time around, so what we're selecting in number 10 is 3 pizzas, right? So, pizza 1, pizza 2, and pizza 3. And the way we order them, in the order in which we place our order doesn't matter. I can say, bring me a cheese, a pepperoni, and a Hawaiian pizza. Or I can say, bring me a pepperoni, a Hawaiian, and a cheese pizza. It doesn't matter. So those are combinations, right? So combinations, order doesn't matter, of 3 what? Not 3 toppings, but 3 pizzas, right? So we're choosing 3 from 3 pizzas. From how many available? How many varieties of pizza? We're asking for 3 different ones, so this is okay. How many varieties of pizza do we have?
2 to the 9.
2 to the 9. So that's here 2 to the 9. So the answer is 2 to the 9, choose 3. So that's the answer to number 10. Yeah.
So why did it choose 2 to the power of 9 from 2?
That was the answer to problem 1, right? The total number of available pizzas.
Makes sense.
Yeah. Yeah. Now, if we didn't have problem 1, you first need to figure out how many pizzas are available, how many different types of pizzas are available, using what we did in problem 1, and then you need to use that as the top of the binomial, choose 3.
Oh, okay. Makes sense. Thank you.
Mm-hmm. And then problem 11, Michael and his friends are planning to buy 1 pizza on Friday, 1 on Saturday, and 1 on Sunday. In how many ways can they do it? And let me just clarify here that the pizzas could be the same, or they can repeat pizzas. You can have a pepperoni pizza on Saturday and also on Sunday. Maybe you want a cheese pizza on Friday. I don't know. Mm-hmm.
2 to the power of 27.
Yeah. Yes. Mm-hmm. So these ones are actually strings, right? Because the order matters. So these are strings. Let me just write here. For number 11, you have whatever you order on Friday, whatever you order on Saturday, and whatever you order on Sunday, right? So these are strings, as opposed to in the previous one, we had combinations, right? And so here I have to write the number of available pizzas for each of those days. And again, we use problem 1. We know that there are 2 to the 9 available for each of those days. We multiply them, and we get Noah's answer, 2 to the 27. Mm-hmm. So this one is 2 to the 9, 2 to the 9, 2 to the 9. If you're not allowed to repeat, if you want to get 3 different pizzas in 3 different days, so let me just say here, if not allowed to repeat, pizzas, you know, if you already had a pepperoni on Friday, you have to have something else on Saturday, and so on. Then we still have the Friday, Saturday, Sunday, but now we have 2 to the 9 here, 2 to the 9 minus 1 here, because we cannot repeat the pizza from the first day, and 2 to the 9 minus 2 here, because you cannot repeat the previous 2 pizzas. Huh? But those are still strings. It's just, you know, I guess here we are in this one. Oops. Ah, okay. Sure. No. Okay. So in this one, in the first one, we allow repetitions. And in this one, we don't allow repetitions. So typically I call them strings with repetition and without repetitions. Mm-hmm. And so in that one, these combinations we're not allowing, we're choosing 3 different pizzas, right? So don't allow repetitions. They're different, right? That was explicitly stated in problem 10. So the question is, what if we allow repetitions? You know, if I just say, how many ways can we order 3 different pizzas? I see, if instead of saying 3 different pizzas, I say just, in how many ways can we order 3 pizzas? But I can actually repeat them. Mm-hmm. We actually have the tools to do that. We just have to kind of use different things from here and there. Let me try to solve that here and that. But give me 1 second before we do that. That will bring me to what is called combinations with repetition, and that's like a completely big different topic. So I'm gonna get to that in a second. Let me just finish with the activity, okay? So suppose you can ask for any combination of toppings for half your pizza and for any combination of toppings for the other half. In how many ways can you order your pizza? Mm-hmm. So here, go ahead.
Is it 2 to the 18?
2 to the 18? Let's see. Let me just write here as possibilities for number 12. 2 to the 18. So that would be because you have 2 to the 9 for one side and 2 to the 9 for the other side. Is that right?
Yeah.
Yeah. Okay, let's see. Let me ask you something. So right now you're thinking that I have 2 to the 9 possibilities here and 2 to the 9 possibilities there, right? Half and half. Let's say that I ask for a pepperoni, you know. Let's say that I ask for a pepperoni. I'm just going to write the P. Pepperoni here. And I don't know what other toppings or what did I have. Bacon, I think. I don't know. Pepperoni, mushrooms, peppers, olives, sausage, salami, onions, bacon. So let's say that I ask for, this is one of my, these are one topping pizzas is one of those, right? The pepperoni pizza is one of those 2 to the 9, and the bacon is one of those 2 to the 9. Is this the same as having bacon here and pepperoni there? Aren't these the same? Should we count them as the same? And I just have to rotate it. They should count as the same, right? because she just told them put on half of it bacon and on the other half pepperoni. Doesn't matter which half, right? So they should count as the same. But the way that we're doing it, we're counting them as different.
So we just divide 2 to the 18 by 2, right?
Oh, that looks like a very good choice. However, if we divide by 2, what happens with having pepperoni on, pepperoni on both sides? So, the same argument, yeah, pepperoni, this should count as the same, but this should count as the same, but they're counted once, right? Twice. By 2 to the 9, right? So, yes, good suggestion. Let's divide by 2. But this are only counted once. These are only the pepperoni pizza, maybe I should say this. This is only counted.
Wait, how is that only counted once if we're choosing for I thought it'd be the same as the first part.
So let me give you an example. So this is counting strings, right? The 2 to the 9 times 2 to the 9 is counting strings. So, I can have, when I count the strings with P's and B's, let's say, let's say I can use P or B for pepperoni or bacon. When I'm doing the 2 to the 9 times 2 to the 9, I'm counting this, I'm counting this, I'm counting this. These are strings. And I'm counting this. Mm-hmm. So this one is counted once. This one, when I translate to combinations, is counted twice. And this one is counted only once.
Mm-hmm. Okay.
This is like the 2 times 2. If I only had 2 choices, I have 4. So there's 4 here. Maybe I should write it here. If I only had those choices, right? Of course, I have 2 to the 9. So, but just to illustrate, if I only had 2 types of pizzas, the pepperoni and the bacon, then when I do 2 times 2, 2 to the first and 2 to the first, it will give me 4 choices. And as you can see, I'm counting the ones with the different halves are counted twice, but the ones with the same half are counted only once. So if I divide this by 2, then I'm actually counting each of these ones only half a time. Mm-hmm. So I cannot divide that by 2. It doesn't solve it. So let me tell you how you can solve it. You can say, okay, if both halves are the same, like the pepperoni on both sides, so both halves equal, yeah? And then if they're not equal, so maybe I should say same halves, different halves. I guess that's better. So I have 2 possibilities, right? I can have same halves, or I can have different halves. If I count them separately, then I'm okay. You see, here, same halves, I only have 2 to the 9, right? Because it's like choosing one full pizza, right? And if I'm using different halves, then I actually have to do 2 to the 9 choose 2, because I'm choosing the 2 different varieties. But the order is not important. So these are actually combinations, right? If I ask pepperoni on one half and bacon in the other, or if I ask bacon in the first half and pepperoni in the second one, it gives me the same thing. So this is accounting for that. These are actually combinations, because the order in which I request them doesn't matter, right? And just notice that this quantity is not 2 to the 9 times 2 to the 9. It's 2 to the 9 times 2 to the 8. 2 to the 9. 2 to the 9 times 2 to the 9 minus 1 over 2. over 2. So, if you actually use the formula for this one, it's actually this. So it's not 2 to the 9 times 2 to the 9 and then divided by 2, which I try to explain doesn't work. Almost, but it doesn't work. So I cannot just divide by 2 because the ones that have only one variety on both sides, the same variety on both sides, are only counted once. So I'm dividing also those by 2, but I shouldn't. So note that this is the argument of dividing by 2, but this already requires that the two toppings are different. So instead of having 2 to the 9 times 2 to the 9 and then dividing by 2, I have 2 to the 9, 1 less, times 2 to the 9 minus 1, and then divide by 2. And then the ones that use the same on both halves, I can count separately. That makes sense?
No, it didn't make sense. Can you repeat it again? Because it didn't really process.
Okay, let me just write something here, just so that I don't forget. So the answer to this one is 2 to the 9 plus 2 to the 9 choose 2. Okay, so let me explain. Because we didn't say that the halves need to be different, you see, suppose you can ask any combination of toppings for half your pizza and for any combination of toppings on the other half, right? How many ways? So the halves could be the same. If you're thinking of a pizza that has different halves, what you do is you're choosing. It's not a strings, you're choosing 2 different varieties because the order in which you request them doesn't matter. That's the 2 to the 9 choose 2. Okay? If your 2 halves are the same, it's the same as asking for one variety of pizza, right? One full pepperoni or one full Hawaiian or one full whatever it is, right? So choosing one variety of pizza, that's a 2 choose 9. So that's the explanation for the final answer, right? Everything else I was saying was trying to explain why some other things don't work. So, this one doesn't work. Almost, it's a good idea, but there is some double counting here for this ones. A pizza like this is double counted. And the thing is that this one, this 2 to the 18, is counting strings. Right? So this is counting strings. So the order is important, but it isn't in our context because these two are the same. So it isn't. So we shouldn't be using strings. If we do, we have to divide by 2, but only when the 2 halves are different. That's why 2 to the 18. So let me write it here. 2 to the 18, which is 2 to the 18 divided by 2, which is the argument 2 to the 9 times 2 to the 9 divided by 2, doesn't work either. Almost. But it doesn't work either because, yes, we are making sure that we're not double counting here, but these ones are not double counted and we're still dividing them by 2. So that's why that one fails. So
it has the same topping, you can't divide by 2.
Yeah, the ones that have, exactly, those you cannot divide by 2.
With the one where it says like pepperoni and bacon, and then you flip the bacon and pepperoni, you're able to divide by 2 there or no?
So this ones you will have to divide by 2. So let me say this. So so this is an example of having 2 different halves. Right? Those we need to divide by 2. But if you already know that they're different, there's only 2 to the 9 times 2 to the 9 minus 1. Because they're different, right? So once I chose this one I have one less choice. So it's not 2 to the 9 times 2 to the 9, it's 2 to the 9 times 2 to the 9 minus 1. And those I do have to divide by 2 because we're not counting strings because those two are the same. So from here, I'm supposed to get 2 to the 9 times 2 to the 9 minus 1 divided by 2. Those I can divide by 2, that's fine. but not the two, but not this, right? Because this 2 to the 9 times 2 to the 9 is also including these ones, and those I don't want to divide by 2. Huh? So
Question.
Go ahead.
That 2 to the 9th times 2 to the 9th minus 1. Is it okay we could just leave it as 2 to the 9, choose 2, or use a calculator?
Yeah, it's okay.
Okay, because I still don't understand the 2 choose 9. No, not 2 choose 9.
Yes?
2 to the 9th power times 2 to the 9th power minus 1, but I do understand it when it's in the form of 2 to the 9th power choose 2. Because it takes care of the each half. It doesn't matter whether your pepperoni's on the left or right side. And plus, you could choose one side and just simply rotate the pizza and it would still look like the other side then.
Yeah.
So,
So these two are equivalent, whichever you prefer. You know, to me, it's easier to use it 2 to the 9 choose 2 because that's exactly the definition of what we're counting, right? When the two halves are different. So that one.
Okay, it makes more sense.
This one.
Thank you.
So if I were just presenting the correct solution, I will just tell you this, right? And that would probably be clearer. But it is important to understand why other solutions don't work so that you don't make those mistakes in other problems, or you understand why those don't work in other problems, okay? All right. So that brings me so we're jumping to something different. So what if we allow repetitions of, when we choose 3 pizzas? So we're going to see combinations, what we call combinations with repetition. So let me start with that. With that problem as our starting point for combinations with repetition. So now I want to select 3 pizzas, not necessarily different. Okay? So I can use, here I'm counting 3 different pizzas, the 2 to the 9 choose 3. What if I'm allowed to have like 2 cheese pizzas and a pepperoni pizza, or 3 cheese pizzas? What if I'm allowed to repeat? Okay, so those are called combinations with repetition, and I'm going to start another page because this one is already super crowded. Here we only did problem 5 and on. Okay. Okay, so imagine that you are, let me get one problem in particular. Yeah. Yeah. So let me go over B23, and then we'll go back to that problem with the pizzas. So B23 says, find the number of 5-letter combinations from, you're allowed to use any letter in the alphabet, allowing repetitions. That's very important. Okay, so they are combinations, so we don't care about the order, but we are allowed to repeat. So it's not going to be 26 choose 5, because 26 choose 5 doesn't allow repetitions. Okay, so let me just say here, note that 26, because there are 26 letters in the alphabet, choose 5 counts the number of 5-letter combinations without repetitions. Like here I can have A, B, C, D, and E. That's a five-letter combination. But here I'm not counting the A, B, C, C. So this one is not counted here. But it's supposed to be counted in the original problem. Make sense? The difference? Huh? So this one is supposed to be counted in B23. But it's not counted. In the 26 choose 5. Okay? So here's the general idea. This is called the stars and bars. This is, I think, something very clever. This is what you do. We're going to count strings of bars and stars.
Oh, can we just use the formula of something?
Yes.
Pick R?
Yes, there is a formula, and yes, you can use it. But I want to explain it to you, like how come you how can you come up with that formula? And so how do you because if you don't know how to come up with it, you won't be able to adapt it, right? And I show you that problem can change very easily, and you should be flexible on adapting your formulas. So I'll show you how that one is derived, and then you hopefully will be able to adapt it to other situations. Okay, so this method will get us to that formula.
Okay, because I thought you already covered that formula. It was basically like NCR, but without the R factorial part in the denominator, basically.
Oh no, that was permutations. Without repetition.
So it's not n factorial divided by n minus r factorial.
No.
Oh, okay.
I'll put them, the four of them together. So we have permutations with and without repetition, and then combinations with and without repetition. So once we finish with this, I'll put the four of them so that you can compare them. Mm-hmm.
Oh, okay.
So here we're gonna count the strings of bars and stars. The bars are going to be the 5 letters. Are representing the 5 letters that we will use. And the stars are separators. You'll see what I mean in a second. Okay, and we're gonna have, sorry. Oh yeah, that was fine. So 5 letters are the bars, and the separators, let me just say how many. Because we have 26 letters in the alphabet, we're going to use 25, or maybe I should write 26 minus 1 equals 25 separators. Those are going to be the separators. Okay? So this is the number of different letters available. Right? Okay, so I have my 26, my 5 bars, and I have my 25 separators, and then I'm counting the number of permutations. Okay, so the number of permutations, or maybe I'll say number of rearrangements, of that is there's a total of 30 objects, so 30 factorial if they were different. But because 5 of them are the same, I need to divide by 5 factorial. And because 25 of them are the same, I need to divide by 25 factorial. This is something we talk about in the second class, I think. You know? So you have the rearrangements, but then if you have repetitions of some letter, you have to divide by that number factorial to account for those repetitions. Mm-hmm. Mm-hmm. Another possibility to see this is I have 30 spaces, and I need to place the stars and the stars and the bars. And I need to place 5 stars and the rest are bars, right? So this is the same as 30 choose 5. That is the same as 30 choose 5. So here we're choosing spots for the 5 bars. Mm-hmm. So you can see it like rearrangements or choosing the spots for the bars, and then everything else is a star. Okay? So I'm saying that this is going to be my answer to that problem. 30 choose 5. Okay? Why? I need to give you the one-to-one correspondence. So if I take any of these permutations, for example, let's say that I take a bar, and then I take three stars, and then 2 bars, and then let's say that I have 20 stars, and then I have another bar, or another star. How many do I have? Oh, let's say like this. I have 5 and 25, right? So I have 20, 21, 22, 23, 24, 25, and my 5 bars, 1, 2, 3, 4, 5. Yeah? So I want the one-to-one correspondence between these arrangements and the original problem. The original problem was 5-letter combinations allowing repetitions. So here's the thing. Because I have 25 separators, I have the gaps in between separators. That's going to tell me, look, here. This part is going to be the number of A's. This part in between separators is going to be the number of B's. This part in here is going to be the number of C's. This part between the third and the fourth is going to be the number of D's. Then between the next 2 separators, that's going to be the number of E's, and so on. So this one over here, whatever number I have, is going to be the number of Z's. This is going to be the number of Y's, and this is going to be the number of X's. And then, the next gap between separators will be the number of W's. Make sense? So whatever is between separators, whatever number of bars are between separators is the number of letters of each kind. So this one is assigned to the combination 1A, 2D's. Again, it's a combination, so it's not a string. The order is not important. An X and a Y. Yeah. And if I give you, for example, the one that I had before, just to go backwards, A, B, C, I need to know which of those rearrangements goes with this one. So it has 2 A's, so that's at the beginning. Then I use a separator. Then a B, then I use another separator. Then 2 C's, then I use another separator. And there are no other letters, so all of these are separators, consecutive separators. So these are 23. So this means 2 A's, 1 B, 2 C's, no E's, no F's, not any of the others, no C's. Huh? So 2 A's, 1 B, 2 C's, 0 E's, 0 C's, and so on. This one was 1 A, 0 B's, 0 C's, 2 D's, 0 E's, 0 of all of this, 1 X, 1 Y, and 0 Z's. Do you see the one-to-one correspondence? Yeah?
Professor, I have
Yeah.
a question. Why are we subtracting 1 from the 26 where it stars?
Oh, because I'm using the gap, this one and this one. I have I'm using one letter for each separator. I have a gap before, right? I have 25 separators, so I have 25 gaps that account for 25 letters before those separators. But I also have this one that's after. That's like an extra one. So this is the 26 letter. So you see, letter separator, letter separator, letter separator. So if I count the gap right before the separator, including this one, that's going to be 25 all the way to here. Mm-hmm. And then I just use the one after for the last letter. So let me say it in a different way. Suppose that you are adding 3 numbers, right? Those are like my bars, the numbers. And the pluses are my separators. How many pluses do I need to add 3 numbers?
2.
2. 1 less, right? The pluses are my separators because I'm counting like the very beginning and the very end, and that kind of counts twice. I don't know. Yeah. So it's like an extra spot. So that's why.
Oh, thank you.
Yeah. So the answer to our question, because we know how to count those, that was 30 choose 5, or the 30 factorial over 5 factorial times 25 factorial. So for this ones, I have that quantity that I said before. 30 choose 5. Mm-hmm. So of these ones, these are the 5 letter combinations. These were the rearrangements. Of the 5 bars and the 25 stars. And these are the 5 letter combinations with repetition. So repetitions allowed. It's the same thing, 30 choose 5. Mm-hmm. And the way that we did it, so where the 30 comes from is the 5, because the size of the combinations is 5 letters. And then we added the 26 minus 1. Those are the stars, right? The separators. And these are the number of letters, right? And then we're choosing the 5. Or 25 if you want, because we know that the n choose k is the same as n choose n minus k. So that's the answer. This is your answer.
Professor, I have a question. What's the main difference between permutation and combination in this case? Because if it was a string, we would say 26 to the 5th, right? So what's the case is different than this?
I see. Look, here we're counting combinations, right? On this side, we're counting combinations. So the order of the letters is not relevant. Here, we're counting strings, even though we got that factorial, right? Here we're counting strings, these type of strings. That's why when we counted, so, because these are strings, that's where the 30 factorial comes from. Mm-hmm. This there's some repetitions. So let me just say there's some repetitions. That's why we are dividing. We're dividing by that. And just almost as a coincidence, we got this binomial. Mm-hmm. Now, you can also see these as combinations if you're choosing these pots for the 5 bars. That's where the 30 choose 5 comes from. Mm-hmm. Now, these are combinations. We're not allowing, I mean, the order is not important, sorry, but we are allowing repetitions. If we were not allowing repetitions, it would just be 26 choose 5. Mm-hmm. Let's see if I can clarify this in a different way. So that you can see the difference. So the comparison of the 4, right? So 5-letter words allowing repetition, or maybe with no repetitions. And everything is from the 26 letters, okay? So that would be strings. 1, 2, 3, 4, 5. 5-letter words. So I have 26 for each. I said with no repetitions, sorry. So with no repetitions, that would be 26, 25, and so on. Mm-hmm. So this one is the 26 minus 5, 26 factorial over 26 minus 5 factorial. Okay, so that was what Sean was talking about earlier. So this is the strings. And now we're gonna have combinations. Here, good. And we're gonna have, so this is no repetitions. Allowed. And here, repetitions allowed. Okay? So we're gonna see the 4 things. So here, 5-letter words with no repetitions, you can have something like, I don't know, B, A, T, T, P. Oh, no repetition, sorry. T, F, P. I don't know. Okay, so we're counting things like that. Here we will have 5-letter words with repetition allowed. So here it is okay to have B, B, T, A, P. 2 of them are the same. I can have more of the same. Mm-hmm. It's also okay to have only A's, for example. But that one, this is included here. So maybe like that. So these are less, but all of these count here. So for that one, that's still strings. So this is 26 times 26 times 26 times 26 times 26. So this is 26 to the 5th. Okay? So now combinations. So 5-letter combinations. Remember, the strings are order. The combinations are on order. So 5-letter combinations with no repetition. So that would be 20, the definition of the binomial, 26 choose 5. Mm-hmm. And here, instead of having words, we have like bags of letters with wooden letters inside. So here I am allowed to have A, B, C, no order, A, B, C, D, E, or any letters like B, A, T, F, P. See, here this one is different from A, T, F, P, B. Whereas those two things are kind of counting as the same when you put the letters in a bag. Make sense? So these are like bags of letters, and those are words. And then combinations, repetitions allowed. Now the difference is that now I'm allowing to have letters that are the same in my bag. But there is no order.
Wait, question? The two F's in that circle inside the no repetitions allowed for combination.
Yeah, thank you. That wasn't supposed to be. I was trying to copy this. B, A, T, F. Oh, there's supposed to be a P someplace. That one. So I was just trying to copy the same letters that I had earlier. Thank you, Sean. So P. Yeah, all of them different.
No problem.
So this one also, it's okay to have the ones that don't have repetition, right? So again, this is a smaller number than that one. All of these are contained there. So this would be 5-letter combinations with repetitions allowed. And this one is going to be, size 5. That's going to be my bars. 26 minus 1, those are my separators, and I'm choosing 5 of them. So this is for the 5 letters. If I had something similar, but now we have, n objects, some more in general, n objects available. That's like the 26 above. And here we want strings of length k with no repetitions. We can also have combinations of size k with no repetitions. We can also have strings of length k with repetitions, or we can have combinations of size k with repetitions. So notice that in this, it's the same order as in my example. And so the difference here will be strings length k, no repetition. That would be n times n minus 1 times n minus 2 until, I finish here. This is length k. So this will be n factorial divided by n minus k factorial. This one is just n choose k, which, the formula says this. This one will be with repetitions. This just will be n to the k. And this one will be size k. That's the number of bars. And then plus n minus 1 is the number of separators. That's like the 26 minus 1. and then I'm choosing K. So maybe I'm just going to remove this and have the formula so it looks cleaner. So this is n factorial over n minus k factorial. And just notice that I'm talking about length. Oops. I'm talking about length here for the strings versus size. There's no length because there's no order. All right? Okay, guys. So we'll leave it here. I'll add some problems, especially the easier side of the problems for section B today to the list. So check it, especially if you know that you're close to being next in the list. Okay, and I'll see you Thursday.
Thank you, Professor. See you on Thursday.
Okay. See you Thursday. Bye-bye.